Hello, my name is Kamal Ramamurthy and I'm a software engineer from the GPU, graphics, and display team. In this video, my colleague Sam and I will present how you can accelerate your machine learning models using Metal. Training is the first step of deploying models on Apple's platforms. The second step is to prepare the model for deployment on device. Finally, the model is ready to be integrated into your application, which is what I will focus on in this video. If you're using Core ML to deploy your models, MPS Graph provides GPU acceleration using Metal. To learn more about Core ML, watch the Explore Machine Learning Models on Apple Platforms video. You may also want to watch the Deploy Machine Learning Models on Device with Core ML video. You can also train your models using frameworks like PyTorch, TensorFlow, and JAX. Check out the Train Your ML Models with Apple Silicon GPUs video to learn more. All these frameworks build on top of Metal Performance Shaders Graph, which is a framework for constructing and running general-purpose compute graphs using Metal. MPS Graph provides low-level control over GPU synchronization and memory, so in some cases you may want to use MPS Graph directly. For example, if your application uses Metal, you can use MPS Graph to sequence ML tasks with other GPU work. You can also share low-level Metal resources such as buffers. If you're new to accelerating machine learning using Metal, check out our videos from previous year's WWDCs. Sam and I will talk about three things in this video. First, improvements to MPS and MPS Graph. Many of these are focused on improving the efficiency of transformer models. So I'll use those models as an example. Second, new features which accelerate FFT-based ML models. Finally, Sam will introduce MPS Graph Viewer, which allows you to visualize your ML models. Let's start with the new features focused on improving the performance of transformer models. Transformers are commonly used in language models to translate, predict, and generate text. The input is a sequence of tokens. For example, a simple sentence like, "The quick brown" is a 3-token input. The language model responds by predicting the next token, fox. This new sentence is repeatedly fed back into the model to generate new tokens. MPS and MPS Graph have new features which enable you to improve your transformer models. These improvements fall into three categories. First, improved compute performance. Next, memory bandwidth savings. And finally, quality improvements for transformer models. I'll start with compute performance. Transformer-based models are made of layers of transformer blocks. Focusing further on the internals of a transformer block, it consists of multi-head attention, normalization, and feed-forward blocks. The multi-head attention block is one of the most compute-intensive blocks. This block computes large multi-dimensional matrix multiplications, which are compute-heavy operations. The input matrix is projected through a matrix multiplication layer to produce a query matrix Q, a key matrix K, and a value matrix V, which are then fed to the scale dot product attention block. This is the heart of the transformer model. There are two ways you can optimize the performance of this attention block. If you look inside the attention block, it's made of several operations. MPS Graph now has an operation which combines all this sequence of operations into a single kernel which executes more efficiently. To use this operation, call the scale.productAttention method on an MPS Graph object. This method takes query, key, and value tensors as arguments. Using the fused STPA operation should enable you to improve the performance of your transformer models. Let's revisit the multi-head attention block so I can show you another opportunity to improve compute performance using these tensors. Here you can see how the query, key, and value projections work for the first token. A matrix multiplication operation projects the embedding vector for query, key, and value. To generate the next output token, we have to feed all the previously generated tokens into the matrix multiplication. This results in recomputing the K and V projection that were already calculated in previous iterations. This cost adds up the longer the sequence length gets. To mitigate this problem, you can cache these projections as they are generated so they can be reused in future iterations. The first thing you need to do is create a K and V tensors which will store the cached K and V values. These tensors are called the KV cache. In the first iteration, the K and V values are computed for the first token and inserted into the KV cache. You can now reuse the cached values so that in the second iteration, you only need to compute the K and V values for the second token. This simplifies the matrix-matrix multiplication into a matrix-vector multiplication. You could append the K and V projections to the end of the KV cache by creating a new tensor for every iteration. But this would use a lot of memory. Instead, you can update the existing tensor in place using the slice update operation. You can then use the slice operation to extract just the portion of the KV cache which has been computed. Let's look at how to do this in code. First, create a placeholder representing the cache. The dimensions of this tensor depend on the details of your model. For this example, I'll focus on just the key portion of the cache, but the value portion works the same way. To be able to update the KV cache in place, you will need to create a variable which represents the current state of the cache. Unlike the results of the normal graph operation, you can update this variable to refer to a different value later. For every token, you will need to insert the key projection into the cache. You can do this using the slice update data tensor method on the MPS Graph object. The start and end arrays indicate where to put the new value. This example appends it to the end of the valid portion of the cache. In this case, the stride is uniform. You can now assign the updated cache back to the original variable. MPS Graph will optimize this to update the cache allocation in place. Finally, you can use the slice operation to extract just the portion of the KV cache which has been computed. This is the portion from the beginning of the cache up to the most recently inserted key projection. You can then pass the updated key cache to the SDPA operation. Once you have made these compute improvements, the memory bandwidth becomes the new bottleneck. The memory required to store the weights for large language models can be in the order of tens of gigabytes. These weights are usually represented by using 16-bit floating point. However, MPS supports quantizing these weights to 8-bit integers to reduce the memory footprint by half. New this year, MPS also supports a 4-bit integer format. This allows you to reduce the size of the weights even further. MPS supports several techniques to map your weights to these quantized formats. Here is an example tensor where the elements are distributed on a number line. For 8-bit quantization, there are 256 possible quantization points linearly distributed along the number line. For 4-bit quantization, there are 16 points. During quantization, the points are adjusted to the closest quantized value. The quantization scale factor can be determined by using the formula on the right. This accrues a slight error, but we end up saving 2x or 4x the memory space and bandwidth. Use the dequantize method on the MPS Graph object to dequantize the values. Another quantization technique uses a lookup table. This technique is useful when your weights are clustered around different areas on the number line. With affine quantization, the quantized values are uniformly distributed, but the input values are not. This causes most of the quantized bits to go unused as most input values clustered around only a few quantized points. You can use the quantized bits better by using a lookup table. In this technique, you choose your own quantized points based on the distribution of your data. You store these quantized values in a lookup table. Then, you assign each weight a 4 or 8-bit index into this table. This way, you get a lot more flexibility while sacrificing only a small amount of performance to look up the values in the table. This method to convert these quantized values back into 32-bit floating point values. Simply pass in your quantized weights and the 32-bit lookup table. You can then reuse the dequantized tensor as usual, for example, as an input to a matrix multiplication. In fact, in cases like this, MPS Graph goes one step further. If your graph contains a dequantized operation on the weights preceding a matrix multiplication, MPS Graph will replace the two operations with a single quantized matrix multiplication operation. This operation will dequantize weights on the fly as needed rather than storing a temporary copy of the dequantized weights. Quantization can save memory and memory bandwidth, but it can also introduce numerical inaccuracies. Now, let me show you two ways to improve the quality of your transformer models. When you quantize your weights, each weight is mapped to a lower precision value. You also choose a scale and optionally an offset to apply to the quantized values when dequantizing. However, applying a single scale and offset value to all of the weights will limit how accurate the reconstructed values can be. Instead, you can quantize blocks of elements individually, each with their own scale and offset values. This allows you to match the scale and offset values more precisely to each block. The code to do this is similar to the earlier example, except instead of passing in a single scale and 0-point value, you pass in a tensor containing the scale and 0-point for each block. So that's it for quantization. Next, I'll show you a different way you can improve the quality of your transformer models using adapters. Adapters are small layers that you can insert into your model, consisting of just a few operations and parameters. When you fine-tune the model, only the parameters inside the adapter are updated. This can be used to adapt a pre-trained base model to a new task. But it can also be used to compensate for error introduced by quantization. You can add adapters to your model using MPS Graph callables. The way this works is each adapter is a separate MPS graph that can be called from the main graph. First, insert calls to your adapters from your base graph by specifying a unique name for each adapter. To do this in code, you will need to define the shape and type of the output the call to your adapter will produce. Then use the call method on your main MPS graph object to add the call to your adapter. This is where you provide the name, inputs, and the output types for your callable. Next, create the MPS graph for each adapter. In this example, I'll create a placeholder representing the input as an unranked tensor. Next, I'll create the output tensor by multiplying the input by 2. Finally, compile the graphs for each adapter into a graph executables. These are compiled like any other MPS graph. First, define the input type to the graph by providing the exact shape. Then call the compile method on the graph object providing the metal device, input types, and output tensor. Now that you have added the calls to your adapters from the main graph and compiled the graph executables for each adapter, the last thing you need to do is map the adapter names to the actual graph executables in the main graph. This is done when compiling your main MPS graph for your network using a graph compilation descriptor. First, create a dictionary mapping the name of each adapter to its graph executable and set it on the descriptor. Then simply provide the compilation descriptor when compiling the main graph. And that's all you need to do to set up adapters. To summarize, adapters and callables let you customize your models to perform new tasks and improve the quality because you can use them to fine-tune your model output. Next, I'll tell you about what's new for Fourier transform in MPS and MPS Graph this year. Fast Fourier transforms, or FFTs for short, convert data-like signals or images from the temporal or spatial domain to the frequency domain. They're a common pre-processing step in machine learning models that process audio, such as speech-to-text models, and models that separate different audio sources from a single track. They can also be used to accelerate certain convolution layers, and they're used in many image processing and scientific computing applications. For example, to extract text from an audio signal, the input waveform is first run through a short-time Fourier transform, or STFT. The frequency spectrum is then analyzed by a transformer model to extract text. I've already described how you can use MPS Graph to execute ML models efficiently on the GPU, but you can also use MPS Graph support for fast Fourier transform to move this entire pipeline to the GPU. The first step is to implement the short-time Fourier transform. This works by dividing the input waveform into multiple shorter views, or windows, which may overlap each other. Each window is effectively an independent signal. In order to reduce the spectral leakage, the individual windows are multiplied by a window function. Finally, you can then use a normal batched one-dimensional FFT operation to compute the STFT for each window. In order to divide the waveform into shorter windows, you can create a strided view. First, set up the shape of the windowed view. In this case, the width of the window will be 512 elements. Next, set up the stride for each dimension. This example uses 256, meaning we skip 256 elements in the underlying 1D array for each step in the second dimension. The final batch dimension is set to 1, but you can use large batch sizes. Finally, you can create the strided view by calling the arrayView method on the input tensor. The best part is that the view operation works without performing any copies by aliasing the memory of the input array, saving memory and GPU time. Now, you can compute the FFTs over all the windows. First, create a placeholder for the strided view data. You will need to load the data out of the strided view ND array and provide it when running the graph later. Next, multiply by the window function. This is typically the Hahn window or a Gaussian window. You can use an MPS Graph constant tensor for this, for example. Finally, you can create the FFT tensor operation. So that's it for fast Fourier transforms. Next, I'll hand the presentation over to Sam, who has some great news for you if you want to get a better understanding of your MPS graph structures.
Thanks, Kamal. Hi, everyone. I'm Sam Colbrand, and I'm also a software engineer from the GPU, graphics, and display team. Now, if you're not familiar, Metal includes advanced tools in Xcode and instruments to help you take full advantage of Apple GPUs. With so much power at your fingertips, your Metal pipelines and AI models that run on-device can be bigger and more complex. However, while you can visualize your Metal pipelines with the dependency viewer in Xcode, it hasn't been possible to visualize MPS Graph until now. Today, I'm excited to introduce the newest addition to the Metal tools, coming in Xcode 16, the MPS Graph Viewer. It's a brand new tool specifically designed for machine learning and AI. Now, you can directly open MPS Graph packages in Xcode and visualize how your operations are connected. Before I jump into a demo, let's first recap how to actually create an MPS Graph package, whether you've been using MPS Graph directly or have been developing your ML models in another framework. If you've created your model directly with MPS Graph, first, compile your graph into an MPS Graph executable, then use the Serialize API on the executable to create the package. New this year, you can now also create an MPS Graph executable directly from a Core ML package. As before, you can then serialize the executable to an MPS Graph package. Alternatively, if you're coming from another framework, like one that exports to Onyx, you can use MPS Graph tool to convert your model. Let's go through an example together. I'm using Mistral's model with 7 billion parameters that was converted to Core ML during this year's Bring Your Machine Learning and AI Models to Apple Silicon video. Now, MPS Graph tool can be accessed through the command line, so open up your favorite terminal and run MPS Graph tool with the convert argument. And that's it. Your freshly created MPS Graph package is ready to go. And now, viewing it is easy with the new MPS Graph Viewer. I've already opened the converted Mistral package in Xcode 16, so let me describe what's on my screen. Starting at the top left are the compilation options. By default, the viewer is showing the graph as is. That is, it's not optimized for any particular device, so the operations should appear the same regardless of the device that you're using. Beneath that is the Operations Navigator, which shows you a list of all of the operations used in your graph. In the middle is the graph itself, and finally, on the right, there's the Operation Inspector, which I'll come back to later. At this level, it's a bit hard to see anything, so I'll zoom in. Now I can see high-level structures, and the further in I go, even more detail. Here I can scroll around and see all of the inputs and outputs for each operation and how they're connected. This makes it easy to visualize and understand the structure of your graph. Now, Mistral is a transformer model, and as Kamal explained earlier, these are made of layers of transformer blocks. Let's try to find them. I'll start by looking for the new scaled dot product attention operator, which should be part of the multi-head attention in each transformer block. I could search for it, but I can already see in the operation navigator on the left that there are 32 of them. I'll expand this group and click on the first one to jump to it in the graph. It looks like this operation has 5 inputs, and hopefully you recognize query, key, and value, which Kamal went through earlier. I'll zoom out a little bit to get a better view of the whole transformer block. And following the connections, I can see the blocks that make up the query, the key, and the value. And even at this level, I can see variables in both the key and the value. I'll zoom in on the ones in the key. And since this model was exported from CoreML with states, it's using a KV cache and taking advantage of the new assign to variable and read from variable operations in MPS, which as Kamal showed, will improve compute performance. Now, to simplify the graph, the viewer might show some operations and variables, like this one, in multiple places. And once I've selected the variable, in the inspector on the right, I can see where it's first created and all of the places that it's used. Okay, so that was one transformer block. How about the rest? Well, just like the inspector, I can actually select multiple operations at the same time in the operation navigator. And just like that, the high-level structure is clear, and I can see all of the layers repeated over and over again. Pretty cool. Now, let's talk about constants. You might have already noticed the green preview shown directly inside the graph, but I can also find them sorted by size in the Constant Navigator tab on the left. I'll select the biggest one, then double-click to open the Constant Viewer. Here, you can inspect the train weights and gain insights into what your model has learned. This can help you to uncover opportunities to optimize your model for better integration on device. However, remember the viewer is showing the graph as is. It's not optimized for any particular device. In reality, the graph that's executed might be different. For example, MPS Graph might automatically optimize operations by stitching them together into a single metal kernel. You can use the viewer to visualize this. Let me show you how. I've opened up an MPS Graph package containing ResNet50, and like before, I can zoom in to see all of the operations and constants. But now, let's see what the graph looks like for my device. In the compilation options at the top left, I'll select my device. Now, zooming in, I can see that the operations have been grouped inside these metal stitched shader regions, which I can expand to see inside. Because these operations are fused into a single optimized metal shader, internally they have no memory overhead, which dramatically improves performance. In general, knowing how your graph ultimately gets executed on hardware can be useful to truly understanding its runtime performance characteristics. And that's it for the new MPS Graph viewer. Now, let's recap what was shown today. As Kamal explained earlier, you can accelerate your machine learning with Metal, using Metal Performance Shaders Graph. It's already used under the hood in popular frameworks, such as CoreML, to give you the best performance on Apple Silicon. This year, new features for transformers can help you to improve compute, with the new scaled dot product attention operation combined with KV cache, memory bandwidth with quantization, and quality with adapters through callables. Fourier transforms can now be computed even faster in MPS Graph with the new strided ND-Array API. And lastly, the new MPS Graph viewer makes it easy to understand and gain insights into how your model is executed on Apple Silicon. Make sure to check out the documentation and sample code for MPS Graph. And of course, model integration is the last piece of the puzzle. So if you haven't already, make sure to check out these other great videos to learn more about training and deployment. Thanks for watching and have a great WWDC.